Let's jump right in. Welcome to this explainer, where we are taking a massive deep dive into the IEEE 1149.1 JTAG TAP state machine, specifically grounded in the AMD UltraScale architecture. If you're a hardware, VLSI, or verification engineer, you know the drill. But today, we're getting into the real silicon-level mechanics of boundary scan and device configuration. We're skipping the basic theory and going straight to the exact timing, protocol accuracy, and physical realities of the test access port. It's going to be a fun one.
Here's our roadmap for this session. We'll start at the physical pin layer, look at the 16-state TAP FSM, map out the instruction versus data paths, dive into boundary scan registers, hit some specific instructions, and wrap up with abort and recovery.
All right, Section 1, the physical interface, the foundational JTAG pins.
So, just as a quick baseline, the core purpose of the Test Access Port, or TAP, is to serially move instructions and data in and out of a component, completely without disrupting normal system operation. Think of it as your dedicated, out-of-band communication channel. It lets us observe silicon activity or test board-level interconnects, totally isolated from whatever the primary system is actually doing.
Okay, let's look at the 4 mandatory physical pins that make this whole operation possible. We've got test data in, test data out, test mode select, and the test clock. Now notice how the standard strictly mandates weak internal pull-up resistors for these 4 pins. That is absolutely crucial to ensure deterministic states if the pins are ever left undriven. Floating pins? No problem. The internal pull-up guarantees the logic sees a high state. Also, look at the timing here. TDI and TMS are strictly sampled on the rising edge of TCK, while TDO changes state on the falling edge. This half-cycle offset isn't just a suggestion. It's vital for preventing hold time violations when you're moving data through a high-speed scan chain.
Now, you have to respect some very strict physical hardware rules here. For instance, if you accidentally hold the program B pin low, your IDCODE instruction might just return completely corrupted garbage, literally just junk data. Plus, your test clock, it must transition monotonically. Any ringing on that line will absolutely double-clock your state machine and completely destroy your scan chain alignment. And hey, if you are daisy-chaining 3 or more devices, you for sure need to buffer TMS and TCK to ensure you've got sufficient drive strength across the entire board.
Moving right along to Section 2, the 16-state TAP controller and its finite state machine architecture. This is where things get really deterministic. State transitions are governed entirely by the TMS pin, which is sampled precisely on the rising edge of the test clock. The whole JTAG standard relies on this very strict 16-state finite state machine. There are absolutely no asynchronous interrupts here. Every single movement is explicitly clocked by TCK and directed by TMS. Because of this incredibly deterministic nature, we get a guaranteed recovery mechanism. This beautifully illustrates exactly why the TRST, or Test Reset pin, is marked as optional in the standard. You can reliably reset the FSM from literally any unknown state using just TMS and TCK. All you do is hold TMS high, pulse the clock exactly 5 times, and boom, you force the state machine right back into the test logic reset state, no matter where it was locked up. This instantly disables all test logic and lets the IC operate normally.
But this brings up a really fundamental architectural question, right? Once that TAP controller actually leaves the run test idle state, how on earth does the hardware differentiate between an instruction opcode and a test data payload? Like, how do we prevent those internal collisions?
Well, that brings us to Section 3, instruction and data paths and their symmetrical state progression. The answer to that collision problem lies in pure architectural symmetry. The FSM uses the exact same state progressions whether you are routing an opcode or payload data. When you exit Run Test Idle, you hit Select DR Scan. If TMS goes low, you drop into the data register path. If TMS stays high, you're pushed over to the instruction register path. And from there, both paths follow the exact same rhythm: capture, shift, and update.
Let's trace those exact clock edges because timing is literally everything here. In the capture state, data parallel loads right into the shift register on the rising edge of TCK. Then, in the shift state, data moves serially on subsequent rising edges. But pay close attention to the update state. The new instruction or data is latched to the parallel output bank strictly on the falling edge of TCK. This falling edge update is the magic bullet that prevents race conditions right before your data hits the system logic.
All right, Section 4, Boundary Scan Architecture Registers. Let's map out the silicon.
Looking at monolithic UltraScale FPGAs, we are dealing with very specific bit widths.
The instruction register here is strictly 6 bits wide. Though, quick aside, you'll actually see that expand in architectures using stacked silicon interconnects. We also have a massive 32-bit device ID register for capturing those specific hardware signatures, and the vital boundary register. Now that boundary register dynamically scales based on the exact number of input-output blocks on the specific chip you're working with.
Let's zoom in on that boundary register for a second. Each individual IOB has exactly 3 bits dedicated to it: an input bit, an output bit, and a 3-state control bit. This physical layout is an absolute must-know for verification engineers building test vectors to check for opens and shorts on individual I/O blocks. By understanding that the 3-state control bit is routed closest to the TDO pin, meaning it physically shifts out first, you can accurately map your serial data stream directly back to the physical pins on your board.
Of course, you don't always want to spend cycles shifting data through thousands of boundary bits. That is the sheer beauty of the 1-bit bypass register. When you're daisy-chaining a bunch of components, this register, which is initialized to 0 during capture DR, by the way, gives you a super clean, single flip-flop shortcut from TDI directly to TDO for any unselected devices. It keeps your latency to an absolute minimum.
Moving to Section 5, Specific Boundary Scan Instructions. Let's look at opcodes and shifts.
So these AMD vendor-specific and IEEE mandatory opcodes are serially shifted into the instruction register during the shift IR state. Just look at the bypass command. It's beautifully simple, all once, just 6 ones in a row. Then you've got EX-test, which hooks up the boundary scan register to the device pins for board-level testing, and that's 100110. And crucially, if you're looking to load a bit stream or access the internal configuration bus of the FPGA, you would shift in the CFG_in opcode, which is 000101.
But what is actually happening on the TDO line while you shift that new opcode in? Well, the hardware parallel loads a very specific status word right into the instruction register. As you shift new data in via TDI, this captured status word shifts out via TDO, starting with the least significant bit. Now, the standard rigidly dictates that the last 2 bits must strictly be a 0 followed by a 1. If you are looking at your logic analyzer and you don't see that 0-1 hit first, stop right there because your scan chain alignment is completely broken.
Finally, Section 6, Configuration Abort and Recovery. Time for some real-world implementation debugging.
Look, sometimes, even despite having absolutely perfect JTAG signaling, your configuration data just loses alignment. It happens. Here is the exact cycle-by-cycle sequence for actively signaling an abort, which effectively locks the data bus into an error reporting state for exactly 4 clock cycles. You pull the read/write pin high, synchronous to the configuration clock. Then assert chip select low, and boom, the FPGA instantly broadcasts a status word right onto the D00 through D07 data pins. During that tiny 4-cycle window, you absolutely must capture this status word to figure out if a configuration error triggered the abort or if your data alignment just completely failed. Those data pins literally transform into a diagnostic dashboard. Bit D07 tells you straight up if a config error occurred. Bit D06, that tells you if the interface logic actually ever received the initial synchronization word at all. If you are ever debugging a failed boot sequence, capturing these specific bits during those 4 cycles is literally the difference between blindly guessing and actually knowing what went wrong.
Post-abort, you've got to return the hardware to a known state. You have 2 choices here. Option A is the surgical approach. You resynchronize by reloading the sync word. You do this by deasserting and then reasserting the chip select pin and just resuming your packet transfer. Option B, that's the nuclear approach. You just pulse the program B pin low to wipe the slate entirely clean and hard reset the entire configuration logic.
Truly mastering this protocol is the key to unlocking real, uncompromised silicon-level visibility. When you understand exactly what the hardware is doing on the rising versus the falling edge of that test clock, JTAG stops being just a simple programming cable and transforms into an incredibly powerful debug instrument. So, knowing how strictly the TAP FSM locks hardware states to specific clock edges, how will you leverage this standard to debug your next multi-chip topology? Thanks for joining this explainer. See you next time.